So our next speaker was due to be Sergio Marchese from One Spin Solutions. Unfortunately, Sergio is not well and I'm unable to make it, but we're going to have an online presentation all the way from Boston instead. So by the magic of webinars and the magic of Sarah, we should have Dave Kelf online.
Well, yes, so firstly, hopefully you can hear me okay. I have to apologize again for Sergio. He was taken ill yesterday. Nothing too horribly serious, but unfortunately he couldn't make it today. So you've got me instead. And but I think Sergio and I have been working on this presentation together, so hopefully I can answer the same questions that he could have. So what we would like to talk about today is an area where I know a lot of people have been concerned for a while, and a lot of companies have been doing a lot of work. This is the area of combining simulation and formal to really kind of create a general or generally applicable methodology for targeting tough verification problems. So, we all know, I think everyone in the room there knows that simulation and formal are both these days very capable technologies for doing different aspects of verification, and the reason is they tend to operate very orthogonally together. And in fact, John mentioned, the formal technology available today and the kinds of things that you can apply formal to is extremely powerful. But you still need a good simulation backdrop to be able to do a complete verification environment or complete verification run. The question is, how can we combine the strengths of these technologies to really solve these complex verification problems? And what can we learn from what people are already doing today? And secondly, how can we do this in a very general method? So rather than the very specific methods that some companies have been able to develop to target specific problems, can we come up with a more generally applicable method and start to tie it into things like UVM flows more effectively than is going on today? What I would like to look at in this presentation is an example that we've actually been working on with a couple of engineering teams and some partners, including actually TBS, and give you just an overview, a sense of sort of where the technology is heading in this regard. So just a quick primer. Again, I expect many of you know this already, but the difference between simulation and formal. If we think of a digital design as basically a piece of logic which can take on a number of different states over a period of time, then essentially what simulation does is allows different states to be transitioned clock by clock as directed by the stimulus that's applied, and it operates essentially in a fairly temporal fashion. So over a period of, sometimes a long period of time, you can complete a large number of states and check the overall operation of a device by doing that. Formal, rather than operating in a more temporal direction, operates in kind of a state space manner, where it can consider all of the states that a design can take on in a particular time slot, and then look at how those states transition over a number of time slots, but clearly nowhere near the temporal level of simulation. So we kind of, you can think of it as an orthogonal kind of operation where formal can target states and state spaces in one particular time or a sequence of a few time slots, whereas simulation can go for a set number of states, but not necessarily an exhaustive level over a long period of time. And so you look at this and you would think, well, gosh, surely we should be able to combine this in some meaningful fashion to really generate a much more highly covered verification problem. And that is really the area that we've been focusing on. A quick overview of sort of the two technologies that we believe are important for this, and again this is not probably very surprising to many of you. Firstly, a method to provide a really good solid framework for the verification plan is absolutely essential. And in our example here, we discuss and we talk about AssureSign, which is the TVS technology in this space, which they're developed, working with a lot of different companies, and we think provides a really good backdrop for this. So you need to provide a really solid plan that allows you to direct different testing activities to simulation to formal. And then the other thing we need is some mechanism, of course, to bring everything together. And coverage, of course, is the obvious way to do this. But there's coverage and there's coverage, and we'll look at that in a second. So what we need to do is bring together the information, which might be somewhat different from different technologies, and feed it back in the form of metrics into a sure sign so we understand how we're doing against our test plan. Again, all this is fairly obvious. The devil is clearly in the details here. How can we set up tests and then tie that into the coverage metrics that we then provide back, and how can we really measure that coverage in a meaningful and sensible fashion? So what we're going to do in this presentation is look at a design. This is a design that actually is a real one that we've been working on with a company in the automotive fail-safe space. So it's a very complicated design. It's also one that requires very strenuous testing. And the requirement here is to produce a memory that is fault tolerant. So if for some reason a bit is flipped in this memory, an error correction code system is applied, which basically returns the data back to what it should have been. And the system around it needs to check so that if it is told that there was an error correcting necessity, then it comes back and runs diagnostics on this memory. So it can figure out, is this a one-off event created by some electromagnetic disturbance, or actually did the memory go down? So this is a very typical type of design in the fail-safe automotive safety-critical kind of space. And as I say, it's one that we've tried to apply this kind of methodology to. So if we take this and we apply it to our basic methodology here, one way of approaching this, and of course there's many ways, but one way might be first to make sure that the memory together with its error encoding decoding system works absolutely with absolute 100% coverage, and we can totally rely that we've done a full test of this. And then secondly, to make sure that that component within the entire system is able to be tested by the system and the diagnostics are able to be run and the fault scenario detected. And then to take the coverage information from each and bring it together in some way and then apply it back to the test plan that we might put in place. So the first thing is to test the component. We would argue, I mean, this can be done, of course, with simulation or with formal verification or a combination thereof. In this particular example, the company doing this used formal, and what they essentially did is create assertions that would specify, and actually the assertion isn't that hard in this case, it would specify essentially for the address of the range that needs to be tested. Let's check all the possible data values and all the possible ways that the data values may be encoded and decoded. And then let's do that with all possible faults that could be inserted in this memory. So this sounds like a lot of states, and it is. However, a good formal tool these days can actually cycle through this kind of verification within like a 24-hour period and give a completely exhaustive test of this problem. Using the assure sign nomenclature underneath, if we wanted to set up a test plan for this, what we would do is we would talk about the different features that we need to apply, and then use that to set goals that you see on the right-hand side, which essentially are our specific tests, essentially. And we can do that using assertions which we based around the goals, and we can think of this as almost as functional tests, of course. And then obviously we would generate metrics along the lines of, firstly, not expect to have a failure, and secondly, a fairly high functional coverage kind of number. So having tested our component and being fairly sure that it's working properly, we would then go on to test the overall system. Now, this is a test which is very different in nature, involves a large number of parts, and no doubt it would involve a large, a lengthy time period of operation as well. So this is ideal for simulation. In fact, the company that did this work used a simulation for this part, no surprise. And essentially what would happen is the alarm bits coming out of the coder, the encoder decoder, would be forced to a certain level, and then the operation of the diagnostic system would be analyzed to make sure that the memory was fully cycled, and that a fault inside the memory, which was seen to be permanent, which you could do by changing the design, would actually trigger the component to be noted as faulty, versus a temporary injected fault, would be noted as something that just has happened because of the environment, and it's not because of a faulty component. So again, the assure sign goals and features would be set up to allow for this, and the metrics that would be fed back, again with a functional nature, would be set up to make sure the diagnostics operated correctly. One thing I should mention is that here, when we're inserting faults, this can be done in both simulation and formal. Because this is safety critical design, we have an issue that you can't just go in and change the Verilog code. You can't change the design and say, well, that's now a fault, let's see how it operates. You've got to inject a fault with the design being the same as it was before. Otherwise, you fail some of the new automotive safety standards like 26262. Which basically says you've got to do all testing without changing any design code. So you need to start to apply some more advanced techniques such as fault injection, which you could do with a Verilog 4 statement, or in formal you can actually apply faults without changing the design and do it with the faults being exhaustively applied across the memory. Okay, so we're testing both our system and the component itself using different techniques here. The question now is, back to our overall diagram, how can we take the information from this and the coverage information in particular and combine it? Because now we're looking at very different coverage problems. So on the left-hand side, we're looking at formal coverage, and this tends to be functional in nature, although, of course, generating a full functional coverage spec for this is hard, but this is the direction we really want to go in. And the second, with the system test, it's now a very closely defined functional coverage problem with very specific coverage objectives having to be laid out and actually included inside the tests. And then all this needs to be combined in some manner. So we would suggest the technique which we've called observation coverage, and actually observation coverage is not dissimilar to some of the techniques that Jörg was mentioning earlier in terms of a system which essentially allows you to test the quality of either a test bench in simulation or a series of assertions in formal verification, or a combination thereof. So the idea is essentially you change part of the design in some manner, and if you've got a very well-covered verification environment, you change part of the design. Theoretically, the environment should pick up that change as a possible fault. And there's a number of reasons why it might not, and any one of those reasons would be something you need to know about as you're doing the verification. The thing with observation coverage is we're allowed to use the power of the formal engine to make this process very efficient. The issue you have with mutation type coverage is, of course, you magnify the number of simulation runs or formal runs that you have to apply, because you have to check a steady design and then a design with lots of different faults all over it. So it's a bit like the good old fault simulation of many years ago. With formal verification, you can, to a certain extent, make that a much more efficient process by replacing the mutation with a free variable. And I won't get into the technology now because of the time we've got in this presentation, but essentially, Quantify allows you to do that. And Quantify is this observation coverage tool technology that we've been applying to this problem. So what we can do is we can use a system of observation coverage, firstly to understand if the code itself has areas that can be tested, or is there areas such as dead code or over-constrained code, things like that, which you need to know for simulation and for formal verification, so it provides an overall coverage framework for that. And then on the formal side, we can actually apply functional coverage type operations, and we can do that. We can do that while also sort of measuring them against the metrics that we need to apply from our test plan. So essentially what we do is we check the code is reachable, we apply a free variable, and then we make sure all the assertions actually create a very full and rigorous coverage, functional coverage scenario for this particular design. So we have that, and then what we want to do is combine that with simulation. And this is really where you get into issues in terms of the types of coverage information being different, of course. So with observation coverage, what we're looking at is the quality of tests that are applied and actually the checks that are applied in a verification environment. And this is similar, again, to mutation coverage that Jörg was mentioning before. So basically, what we want to do is combine these different coverage techniques, and the way we believe to do this is through this standard that the Celera has created called Unified Coverage Interoperability Standard, or UCIS, that I believe many of you would be familiar with. So UCIS is an effort to bring together coverage information from a number of different sources and different companies and tools, and to create one set of well-structured metrics that can be provided back to the planner. And we think it's an absolutely vital direction to go for the industry, and really want to support this whole UCIS effort. So what we found today is UCIS is very well equipped to handle all kinds of simulation type information, the structural coverage, line coverage, code coverage, all these other forms, but it needs a bit of work to handle some of the observation coverage techniques. And the reason for this is a lot of the coverage techniques that are applied today tend to be focused around stimulus and around making sure a design is exercised, not so much making sure that the checks that are applied in a design cover the design properly. So they don't look at the checkers so much, they tend to look at the stimulus, in short. However, what we can do is we can take observation coverage information and we can convert it so it actually does fit into the current UCIS standard quite well. And by doing this, what we're able to do, as you see from the central part of this slide, is take the information such as design parts that can be reached and have been reached, and mark that as into the UCIS covered bins as something that has been covered. We can also take parts of the design that have been covered and put it into the covered bins. And then, of course, areas of design that can't be observed in any way, we would put into a coverage exclude bin using the UCIS names here. So the idea here is that we can take UCIS, which is somewhat stimulus-oriented, and we can build up the picture of how that of how the inputs to the design, how the stimulus actually does cover the design in a pretty universal fashion. And we can combine that with the structural and the code type coverage techniques that we see in the simulation today. Ideally, we could extend UCIS now to talk about the kinds of checks that also need to be covered. So increase the idea of the covered bins and coverage exclude there, add to that information about the checks that have been covered as well as the design being stimulated. And so as a future enhancement, that would allow us then to enhance the metrics going back to the verification planner with the sense of functional coverage, essentially. Have the specific functions that we describe actually being tested as well as the design being stimulated. If we can do that, and this is a direction we're going in, and we already have a way of combining this on top of UCIS, then what we can do is close the loop, if we go back to this side, with functional coverage information, which is particularly aligned with the kind of information you would have in your test plan. So what we're able to do is take functional coverage and apply it to the test plan and complete this loop. And we believe then this allows us for a much more rigorous method to combine both formal verification and simulation for doing these kinds of tougher verification problems. So this is a technique that's actually being used now in 2 or 3 places, and we're continuing to expand it. And I think through the year we'll see more work going on with this, both from ourselves, but also I think with other companies as well, looking at this solution. And ultimately, the hope would be that we can come up with a more general purpose mechanism whereby formal can be layered into a UVM system Verilog type simulation environment to target very specific areas where formal is more useful, and the coverage information being pulled out and being fed back into UVM with the verification planning environment around that. And this is the overall idea. So if I go to the end here, so basically the advantages of formal can be traded off, as we've seen. The secret, we believe, to a solution would be both a really concise, powerful framework, such as the TVS AssureSign one, for describing the verification plan and directing that to different tools, and then tying together the coverage information using more functional coverage techniques, such as observation coverage, and using standards like UCS to pull it all together. And a lot of this is available today. AssureSign, observation coverage, UCS are all available and work to a certain extent and have been worked have been used by a number of companies. But some useful additions would be greater support of UCIS, of course, and an extension to UCIS that gives us more of a direction in the functional coverage area. So that's the end of the talk.